Okay. Okay, so the first type of problem we consider, we will see how to prove the non-existence of a limit. More precisely, we are given a function f of two variables of this formula. Okay, here x squared plus y squared. Okay, then we need to prove that the limit of the function f does not exist when x, y tend to the point 0, 0. Okay, so before doing this problem, I would like to recall you this very important statement from the lecture note. If you can show that the limit of the function f when x, y tend to a limit point a, b along a path c1. A path c1 is a line or curve or anything or any continuous path on the xy plane that pass through the point AB. Okay, it's different from the limit of this function when xy tend to the same point but along a different path c2. Then you can say that the limit does not exist. Okay, of course the limit when xy tend to AB does not exist. So based on this statement, to do the problem one, we need to choose two different paths, c1 and c2, right? So let me do this problem as an example for you. So for the path c1, I choose the line y equal to x. You can see easily every point in you can see this the graph of this function go through the point a, point 0, 0, right? And I only take half of it by taking only positive value of non-negative value of x. Okay, so now let's consider the limit along this path c1. Along this path, that means y and x should satisfy this relation of y of the function y equal to x. So you put y equal to x into the formula of the given function. And of course, when x, y tend to 0 along this path, that means x tend to 0. And furthermore, it should tend to 0 from the right, because I only consider x greater than or equal to 0. Okay. So you see, it is not difficult to have that. Right. And now here is the reason why I consider only the non-negative value of x. So I can break the absolute value, and it gives me this number. Okay. So you can stop me if you have any question, right? For the other part, I will take y equal to 2x, and again x non-negative. And similarly, I can find the limit along this path into 0, 0 along the path C2, it will give you the value -1/2 square root of 3. It is not difficult to find this limit. And you can compare the two values and they are different, right? So using the previous statement, you can say that you can conclude about the non-existence of the limit. Okay, it is clear. Okay, so let's try with problem 2. Prove that the limit of the function f x y when it's tend to 0 cannot exist. So I will give you maybe a few minutes to do it. And let's remember that if you can answer the question on the lecture, then you will get the bonus point. Okay, so maybe 2 minutes.
Can you read again the question, please? My headphone is running into some problems.
You mean the question of the second problem, right?
Yes, yes.
Okay, so we need to prove that the limit of this function when x y tend to 0, 0 does not exist. The same question as the first problem.
Thank
Okay.
you. Thank you.
So anyone can give me the answer?
Can I?
Yeah, sure, sure.
So I choose first.
Okay, so please give me a second. I can note the name.
Trần Thế Trung.
Yeah. So I can give you the bonus if you can answer the question. Okay.
Okay.
Okay. So yeah, let's continue.
So first I choose y equal to x squared.
Okay. So the first part, right? Y
Yes.
equal to x squared.
Yes. And then
And,
f
we need to compute the limit along this path, right?
Yes.
We
Equal
write on C1. So we put y equal to x squared into the formula of the function, right?
yes.
So what is the formula here?
Is x to power 4 over 2x to
power 4, right?
yes, and is
And
equal
x
to
is 0. And
yes.
this one is 1/2, right?
Yes.
Okay. So what is the C2?
The C2 will be y equal to 2x squared.
2x squared. Yeah, it's very, very good. So what is the value of this limit along C2?
1 over 5.
Yeah, I see. Very good. Thank you. So you don't need to choose a complicated function. Just to the one you think is the most is easiest to find the limit. So you see here the two values are different, so you can conclude about the non-existence, right? Of course, the non-existence of the limit. Okay, I think you get the idea of this program. So we can move to the next part about the continuity. So in this part we will have the problem about the continuous extension. Okay. So before going to this problem, I want to show you what is the continuity of a two variable function. Okay. The function of two variable x f x y is called to be continuous at the point a b if you have this relation. Okay. You can interpret from this relation two conditions of continuity. First, look at the right side. You have a function f at ab. That means the point should belong to the domain of the function. So you can define the value of the function. Okay. Now let's look at the left side. You have a limit, right? So the limit of the function when x, y tend to ab should exist. So that is the most difficult part of proving the continuity. You should find the limit of this function. And the last condition is the value of the limit should be equal to f at ab. So if you want to prove the continuity of a function at a specific point, you need to verify the three conditions. Okay, so now take a look on the problem 4. We are given a function of two variable, which has this formula. Okay. So it is easy to see that this function is not defined at 0, right? That means 0, 0 does not belong to the domain of the function. They are asking us to define. Note that we need to define the value of the function f at 0, 0 to make it continuous at 0, 0. So that means we need to find the value of the limit of function f when x, y tend to 0, 0. And after finding this limit, we can define the value of the function f equal to this value. So you can, that means you already extend the function f continuously to the point 0, 0. So the main step of this problem is to find this limit. So let's think a little bit about how to find the limit of this two variable function. It's quite different from the problem of finding the limit of one variable function, where you have many tools. Someone can give me any idea how to find the limit? Okay, so let me ask you a question. May I choose a particular part? Let me denote it by C1, which pass through the point 0, 0. Then find the limit of f along this path. May I do it? To conclude about the limit. How do you think about this idea? Okay, so anyone can answer me this question. You can get the bonus point. Okay, so I will give you 2 minutes to think about my question. Okay. Anyone have answer? This is very important. It is very important question about the limit of multivariable function. No. So the answer is not. We cannot use the value of the limit along a particular path to conclude about the limit of function. The reason very easy. You can take remember about the first two problem. You know that if the limit along two different paths are different, then the limit does not exist. So we cannot use one particular path C1 to conclude about the limit of the function. However, you can do as follow. First step, you can also choose a particular path C1 to find the value of the limit along the path, and use this value to guess the value of the limit. Here's the limit of the function f when xy tend to 0, 0 in general. This is a very important step if you want to use the definition of limit to conclude. Okay, that means we can follow this scheme to use the definition of limit to find the value of the limit. Okay, that is the first way to do this exercise. The second way to do it is to use a suitable transformation to get an easier limit. By easier limit, I mean the limit you can prove easily the limit, the existence of limit and the value of the limit. Of course, this method is very how to say, very general. There is no exactly step to follow. It depends on the form of on the formula of the function and of course the problem. So let's take a look on what we can do with the problem 4. Let me rewrite the formula. Okay, so when you take a look on this, you see we have x squared plus y squared. And whenever you see this expression, you can think about using the polar coordinate. Okay, let me show you how we do it. So let's recall a little bit what is the polar coordinate. Here I represent the point xy. So this point has the coordinate x and y in the normal coordinate. So how can we change it to polar coordinate? So I denote the distance from this point to the origin by the variable r. So we have r already greater than 0. So from the geometry, we can find easily x equal to r cos of phi, where phi denotes this angle, and y equal to r sine of phi. That means we already changed from the normal coordinate to the polar coordinate. This one is a 1-1 identity. Okay. So let's plug this transformation into find the new formula of into the formula of the function to find the new form. You will get so I just write out here the last formula. The reason I told you, when you see the x squared plus y squared, then you should think about the polar coordinate, because if you use this in this transformation, you can see x squared plus y squared is nothing but r squared, right? So with r squared in the numerator here, I will show you here. You can eliminate it. So now the limit of the function fxy when xy tend to 0, 0. Okay, so let's take a look on it. Take a look on this. You see, when a point xy tend to this origin, that means the distance between this point and this point become to 0, right? So it is equivalent to the fact that r tend to 0. That means r tend to 0. More precisely here, we take r all the way non-negative, so this should be r tend to 0 plus. So using the new formula you have here, okay, and you can see easily this part of phi always bounded is always bounded by 1/2, right? Because the sine and cosine is bounded by 1. 1 and minus 1. So using the Squee theorem, you can see easily when r tend to 0, this function tend to 0. Here is the conclusion from the limit of one variable function. So that means we already find the limit of the function f when xy tend to 0, 0 equal to 0. And to finish this program, we need to do the last step of defining the value of f at 0, 0 equal to 0. That is the one we want to define. Okay. Do you mean I have here a question, the Cartesian coordinate? I mean, it is xy coordinate, if I'm not wrong. And yeah, and the one I use here is polar coordinate. So if you see a problem with a 3-variable function and you have an expression of this type, you can think about this very similar. You can use very similar idea that you can use a sphere. If I'm not wrong, the sphere coordinate, the version of polar coordinate for the 3-dimensional function. three-dimensional space. So is there any question about this problem? Sure, we can still use a we can use the path method to solve this problem. What I already mentioned before. You can see here. I have here some private question about using the path method to find the limit. If you want to use the path method to find the limit, you should follow this scheme. You can choose a particular path you want to find the limit along this path, and then use the value you can get to get the value of the limit. And yeah, you can use the definition of limit to conclude the limit of the function. I have also another question that is very good. When I transform xy into r and phi, you mean I still have a two-variable function. However, the limit only depends on one variable. Sure. The function still have a two-variable. However, the limit only depend on the distance between the point and the 0, 0. When we talk about the new variable, I mean here we change from xy to r phi. We have two variables, and when we say about xy tend to 0, 0, it is equivalent. In general, it is equivalent to the fact that r tend to 0, and the chain of phi will correspond to the chain of the path, which to the way the point approach 0. When you consider this limit, you can see the value of it can be computed independent of phi. That means for every phi, the limit is always 0. So that means the limit is 0 for any path which go through the point 0, 0. So is my answer clear for all of you? It's fine. Okay, so Let's use the same idea to do quickly. The problem 6. We need to define the value of function f at 0, 0 to make this function continuous at 0, 0. Okay, maybe 3 minutes. So what is the value of f at 0, 0? Okay. So it's very similar to the previous problem. It should be you should use one of the two methods I mentioned. Yeah, to find the limit of a function when x y tend to 0, 0. Okay. So you see we have here x squared plus y squared. So it reminds us about using the polar coordinate, which I prefer. However, you can use the definition of limit on the other transformation you can think about. So again, I take x equal to cosine of phi, y equal to r sine of phi. Got phi belong to let me see, 0 to 2 pi, right? And r is positive. Then the function can be rewritten as 3r power 3 cosine square of phi multiplied sine of phi over 2 r squared, and it give us this. Okay, so you see the limit of this function correspond when x and y tend to 0, 0 correspond to the limit of the function of r and phi. Let me recall that we still have a two variable function of r and phi, but the limit depend only on the limit when this point tend to 0, 0 only depend on r. Okay. And this one is not it's not difficult to see the limit equal to 0 because the part of phi is bounded. So the limit equal to 0, that means you should define the value of f at 0, 0 equal to 0. So the last problem I want to do the problem 8, for which we should use the definition of limit. We are given this function. So let's use the definition of limit to prove it is continuous. At origin, that means at 0, 0, 0. Let's think about it. So for the other student, you can continue about thinking this about this the problem 8. So let me answer a private question from a student. So you asked me if for the previous one you have a 0 less than or equal to x squared over 2x squared plus y squared plus 1 less than or equal to 1, right? And you say that you have x squared multiplied with 3y over this one less than 3y greater than 0. First, let me say this implication is not true because you don't know the sign of y. So this inequality in general is not true. Here you are using the square theorem for the two variable function, right? I'm not sure if it is correct. Because in my, I think we only have a square theorem for one variable function, right? Yeah. As far as I know, we only have we only have the version for one variable function. So I think you should not follow this method. Okay. I hope that my answer satisfy you. Okay, so let's come back to the problem 8 because we are going out of time. So the main difficulty here is we need to use a definition, right? That means you should care about the two difference. The difference of the function f and the value at 0, 0, which is 0, and the second difference is the distance between the point x, y, z and 0, 0, which is given by the square root of x squared plus y squared. and plus z squared. That is the distance between this point and the origin. It is defined by this. Okay, so let me recall that the statement of the definition. So for arbitrary epsilon greater than 0, we need to find a number delta depending on the epsilon, such that we have this relation. If the distance from the point xyz to 0 less than delta, then we have the distance between the value of f at this point and at 0, 0 is less than epsilon. So let's see what is this one. It is equivalent to here we use the formula of the function f, right? So it is equivalent to the square root of it less than square root of epsilon, right? So you can see if we choose delta equal to square root of epsilon, then you immediately have this statement, right? Is clear? Is clear? Okay, so if you have no question, we can finish the class here. Okay, so I forgot to take the screenshots. It's not good. So please give me a minute so I can take the screenshots. Okay, so we can finish this lecture here. You can leave. So see you next week.